Hello, welcome to the New Stack Makers, a podcast where we talk about at-scale application development, deployment, and management. So you know how we think about the cloud. Compute, storage, networking, processing lots and lots of data. But what happens when you're collecting data and processing data across a distributed architecture that looks more like an endless fabric of nodes? That's where it gets different. That's where you have to think about it a little bit differently. And a topic I explored with Chris Sachs, founder of Swim.ai, in this episode of the New Stack Makers. Joining Chris is Simon Crosby, the CTO of the company, who helps explain with Chris about this need to squash this processing reality that we see in cloud-based computing and thinking about it more in this distributed way. How do you quash it? The Swim approach is a bit different. And just on a final note, the New Stack will be live at the Cloud Foundry Summit, KubeCon, and Cloud Native Con, as well as OpenStack Summit and ChefConf. We'll be podcasting, hosting pancake breakfast, and spending a lot of time talking with people. We hope to see you out there. Thanks to all our sponsors who make our work possible here at the New Stack. Okay, so I would love to get a demo of the software that you guys have developed. Now, taking what we just discussed as context, how does that set up Swim.ai?
Well, Swim... So first of all, how on earth could one ever go about dealing with vast amounts of data in situ on what might be pretty wimpy edge devices? And by the way, much of that data will be gray because there are trillions of dollars of assets in manufacturing and other types of stuff out there, which are, using arcane protocols and whatever else. And so what one has to do is formulate a method for statefully learning on the fly from vast amounts of gray data without a deep semantic understanding of the thing that you're trying to analyze or predict the future for, and do this on the fly at scale. And Swim does this. Swim is the brainchild of Chris. And so, he will go into the detail of how that works. But essentially, Swim implements the distributed actor framework in an extraordinarily efficient and elegant way. If you know what that means, you're familiar with Akka or Erlang or maybe Orly. And so Swim, instead of saying, hey, it's big data, there's a database someplace, Swim says, yeah, all these digital twins, these actors, they all have their own state. And so we don't need to send squads of data around or store it or save it forever. And then we can start to learn. Chris, why don't you dive in?
Yes. So I'm sharing my screen. We're looking at a live view of the city of Palo Alto. And what we're seeing is the distillation of 50 megabits per second or about 30,000 events per second of raw sort of control plane data from the traffic system in the city of Palo Alto. So every traffic intersection, has a handful of traffic lights and pedestrian buttons and vehicle sensors in the road, and they spew out data. They're just spam bots, right? They spam their state at an incredibly high rate, and it's very difficult to make sense of. And so what Swim's approach to this problem isn't to store all the data that's sort of ever been generated, because kind of who cares what the state of a traffic light was on some 3:35 and 46 seconds on a Tuesday in February or something. The goal is, how do you learn what's happening in this system without having to pay the excruciating transport and storage and analysis costs? And Swim learns sort of very in a similar way to how you and I learn. So what we're doing in this demo, you're actually looking at there are 200 neural networks in this picture, each learning, becoming a domain expert of sorts in one particular intersection. So we have a domain expert, we have a neural network. with about 20 megabytes of learned weights. So that's 20 megabytes of code that a human, would have had to write but didn't have to write. That's trying to just predict, say, hey, can I predict the future of this one traffic light, which is not on a timer, which is highly chaotic and dynamic? Can I predict the future? And it does this in a unique way, rather than, again, collecting and storing the terabytes of data that it generates per day, which would be an unacceptable cost to pay to know the state of one traffic light. Instead, what we've got billions. This traffic light has billions of clock cycles to spare in between network packets, so it uses those clock cycles to make a guess about the future. It just makes a random guess about what it thinks is going to happen next. Then, of course, it observes what actually happens. It gets to measure the error between what it thought would happen and what actually happened and correct for that error. And so without remembering everything that happened, it's able to learn what the patterns of what happens and predict the future.
So basically, it has all these excess clock cycles, and it's just using those clock cycles just to guess, basically. And it just keeps guessing and guessing and guessing and guessing.
Oh, no. Whoa. Not quite.
Well, okay.
The awesome thing is that every data sample is both a training input and a predictor input. So every data sample comes through, and if we're any good at what we do, then the prediction that comes out should match what we see in the real world. If it doesn't, there is an error. The error can be back-propagated through the neural network, and then the next guess will be better. Okay? So every single data sample makes the world better. And the net result, by the way, you're looking at Palo Alto, some of those predictors have done trillions of training operations now. So they're damn good at it. They're really good. By the way, there's another totally awesome thing about this, and that is the following, that we have a neural net per intersection, because each one of those intersections is learning to predict its own future. And the neural net is highly specific to the intersection.
So tell me,
placed on planet Earth. Yeah.
Yes. So tell me about your guys' views on neural net technology and its development, and how it is evolving now, and what is that connection, that intersection, so to speak, with Swim.ai.
So there's a lot of sort of voodoo around like machine learning and neural networks. Like what I see are matrix multiplications with like sinusoidal, like sigmoidal function activation. Neural networks are not complicated things, and they're a tool like many others. And the key thing with learning isn't the algorithms. I feel like there's a lot of attention that's put on algorithms. Learning is all about data and getting the best data sets and the best training samples. Google has sort of a leg up in learning, not because they have the best algorithms. They're using the same matrix multiplications as everybody else. I mean, of course, they have some sort of hardware advantages that they're pursuing, but it's data that is key. And Swim's approach isn't, it's not. You don't need some fundamental new algorithm. There are certain engineering tricks you can employ to make them work phenomenally faster in an appropriate way for an edge environment. But the key is to go to the places that have the data. And most of the data that's generated in the world is trapped. It's trapped in the edge by physics. So I would argue that 99.9% of all data that's ever generated is immediately thrown out.
So
right?
Okay. Mm-hmm. So how do you deploy this? How is an architecture like this distributed? How does it cover, a network of nodes? So
that's a perfect question. So first of all, Kubernetes is not needed, right?
Mm-hmm.
That is, the whole notion of DevOps, which is a very valuable construct for the cloud, is fundamentally anathema at the edge, where you have normal humans trying to make normal things work better who don't know how to run Kubernetes, okay? So Swim builds essentially a mesh of compute, a peer-to-peer mesh, which is self-regulating, resilient, load balanced, and which naturally migrates processing to the right place. So wherever there is capacity, wherever the devices are or the data is that needs to be processed. And so Swim is an edge data processing cloud in a box that just runs, okay? And we know that Swim scales. It does billions of events a day, and just runs forever. And that's a nice property of the this actor model, is that it composes beautifully and naturally, and it scales very well. So how do you deploy it? You could deploy it to the edges. It's user mode software, so you could just stick it out in the edge in a container. You could embed it in a device if you wanted to go down that path. You could stick it in a VM. You could run it in the cloud in a VM. It doesn't really matter.
So Swim looks at the edge is just a bigger version of your multi-core CPU on your machine. And so in the same way that you don't really worry about, how does Microsoft, Word know which core to run on your laptop? The answers are sort of deep and technical and have to do with cache coherency and load distribution. But you take a first principles approach to the edge is a giant, billion node CPU. And the first thing you have to accept is that you cannot decide where the compute runs. You need to build your application logically as sort of this web of interacting processes. And you need to dynamically map those processes to the available hardware. And Swim solves that problem in a very fundamental way. That's similar to how an operating system sort of determines how to map, your video game to CPU cores.
Okay. So then further explain the parallel then from that PC to the world as we know it, and how we make sense of that.
Right. So the other aspect of Swim's approach to this kind of world computing is first sort of our first step is to try and model the world. So the goal is you have sort of physical things in the world. Some have sensors, some don't. But you want to build a model, sort of digital twins, as they say, of the world around you. And we have methods of sort of deriving entities from the environment based on data streams that we observe, and we connect we link these models together in real time. So these in a peer-to-peer fashion. So we're looking at traffic intersections in Palo Alto. Each has sort of a logical digital twin, even though there's actually no physical thing. It's a traffic intersection, right? It's a loose assembly of concrete and a hodgepodge of sensors and a whole bunch of chips. But we created a logical notion of a traffic intersection, and the intersections link together. So each intersection is observing in a peer-to-peer fashion all the other intersections within, in this case, a kilometer radius. So we sort of personify the world and say, okay, I'm in the intersection. I look around. Okay, I've got 4 signals and 8 sensors. I detect this from my environment. Okay, who's around me? Okay, there's 8 other intersections within a kilometer radius, and I gossip my state to those intersections, and they gossip their state to me. And Swim again does this in abstract and automatic fashion, and then we go about our business. What is our objective here? In the case of Palo Alto, it's our default objective is if we're not given something specific to do, we'll just try and predict the future. Sort of training neural networks is kind of the thing to do with spare compute cycles. It's like do other more important stuff first, and then what else do you have to do in those billion clock cycles? But train.
So who out there is also curious about these quadrillions of clock times? Like who?
Well, there are
lots
of people trying to deal with edge data, but most of them are taking some blobs of stacks used elsewhere, say Kafka or something or other, and really wrapping those blobs with a lot of professional services to write custom apps. I think the key the key challenge in addressing the edge opportunity is that there is enormous diversity on a per customer or per use case basis. And unless you're going to put a large number of programmers or professional services folk to work to write custom code each time, you're in deep trouble. And so what we've done is we've invested a huge amount of effort at actually taking any old data and delivering powerful insights from that, which I guess you could think of as hello data, the equivalent of hello world, just from the data without any real semantic knowledge of the thing or the things that are reporting in the data. So the code that predicts what a traffic light or an intersection is going to do can also detect when batteries which are being backed up are about to fail. Okay?
Exactly.
Without really knowing about what those things are. The bit which is, there's an interesting challenge, by the way, which is how do you then associate semantics with that? And I think we can't do that without soliciting the help of users, of humans who can annotate things and we can remember them and learn from that. That is, we've got to try and extract knowledge, semantic knowledge, tribal knowledge from the humans whose job it is to make sure that things continue to run. And we're at the earliest stages of that. We're just focused until now on just dealing with lots of data.
So in the context of Palo Alto, we have a model here that's continually to evolve. And
absolutely,
and that model will continue to evolve just as the models you can have for any other locale or.
Oh, well, actually, it's even cooler than that. For Palo Alto in particular, you have 200 models, each of which is one intersection. Each intersection is learning its own model, given its own data, plus correlated data around it, and that turns out to be the intersections around it, which determine its future to some extent. So you have these 200 models which are independently evolving. Each one of these digital twins presents a real-time API. You can ask it to tell you, or you can query it and say, "Hey, what do you think the world's going to look like in a while?" And on we go. Now, the key thing is this: imagine I sat you down at an intersection, Palo Alto, and I said, "Write me a program for how this thing behaves." Yeah, good luck with that, but it's a hard problem. The problem is, in general, it's a big challenge to do this. That is to come up with programmatic representations of how real-world things behave. The cool contribution of Swim is that we built that program just from the data without humans. And now we can go to it and we can say, well, what if I change this thing or that thing? Right? So you can start to do some interesting things in terms of causality.
And so this is exactly. It's a different kind of learning. We're learning. So what all these disparate systems have in common is that they evolve through time. So the edge sort of calls for a different style of learning than usual. Sort of take a data set, label some data, and then train a model to classify it. What we're doing is self-training to predict causality. And what's great about that is, so we're showing you an example here for traffic. That's what we can make public. But the pattern, the exact same method of learning and sort of pattern recognition works that works for traffic also works for networks, for data networks, or looking at the patterns of human behavior and sort of Wi-Fi radio issues and how a computer network works, or how an industrial control network works, how motors interact in an assembly line. And so this is a very general problem of sort of how sort of physical systems work in the world.
Because essentially a node can be anything.
Exactly.
It can be anything. The interesting thing is that you can learn a program and capture very subtle behavioral information in this program without knowing about it. So, for example, if let's just say you had a widget, I don't know, some industrial manufacturing machine which is producing yogurt, which for Americans is yogurt, and at 5 a.m, the pipes go thud and there's a 10-second blockage or something. That's in the model someplace. but nobody may be aware of it. And so you get this opportunity to learn these potentially important but ephemeral things which affect the behavior of a particular instance of a thing. Much of the discussion in the learning world today is how we will compose models centrally and then distribute them to the edge. The problem with that is overfitting, perhaps even underfitting of data. And so the models are fragile. In the swim world, the models are extraordinarily robust because we're just worried about a model that applies to one particular thing on planet Earth, not to a broad class of things. So we don't have. Go ahead.
Quick question then. So tell me then about how you collect the data and then analyze it. Tell me about the technology that you've built to do that.
So the stack is vertically integrated, and so we have somewhat of a contrarian view in that I believe that vertically integrating software is beneficial as vertically integrating rockets. So each of the pieces is designed very carefully, to fit together and sort of minimize redundancy and maximize efficiency. And so I brought up, the sort of latency of networks being a problem in kind of stateless systems, where a traditional cloud system or even edge environment, you have requests to a database and message broker, maybe some caches along the line or an application server. And each of those network hops is milliseconds or tens of milliseconds. Meanwhile, the CPU is spinning at, on nanosecond timescales. Those are those billions of billions of clock cycles that add up. Right. And so Swim squashes the entire sort of software stack that you'd find in a cloud environment into a sub 2 megabyte software kernel that is uniform on every node and contains storage. It contains networking. It contains sort of process management. It's pervasively back pressure regulated, both for adjusting to variable network speeds and storage speeds and memory speeds. And it aims to just go as fast as possible, but no faster. To use every network packet to its advantage, to use every compute cycle to its advantage. And so in leveraging that requires sort of very comprehensive knowledge of what the hardware is doing, what the application is doing. So having a vertically integrated approach, you have sort of complete visibility into the application, which allows you to automate the management and distribution and balancing of that application without users having to do it. And users and developers, you can't know how to do it. On the edge, every edge environment is different. Whatever architecture you pick for the edge, it's going to be wrong for most environments. You have to make these decisions autonomously and at runtime. It's the only method that will scale at the edge.
Autonomously in that runtime, and that's why you squash it so much.
Yeah, so we have all of the knobs at our disposal to turn without having to loop a developer in.
So it's fully configured.
It's fully self-contained. We can run as the init daemon on a Linux kernel. We can run without a kernel if we have something providing us I/O. It's a raw compute platform.
So it could be used with an application architecture then?
Yes. Sure. It's designed to be self-sufficient and standalone, but it works quite nicely with others. We have protocol bridges for standard protocols, and because we're unimposing, we fit in elsewhere. We run the entire Swim stack in like log daemons, for example, and other application servers. So you can actually, our stack is smaller. Our entire stack, including database and distribution management, is smaller than your average logging adapter for, say, the Java virtual machine.
So you're doing logging essentially at this quadrillion level. So if you're doing this type of data collection, how are you analyzing the data at the edge? So is it just continually indexed within the node itself for that essence?
So for job number one, given dark data or gray data, is to figure out what the hell the thing the things are that are squawking at you. Okay,
Yeah.
so there's a whole layer which Chris hasn't described, which is inferring a schema on the data, because we don't know whether it's a battery or a traffic light or whatever, and we don't have any notion of behavioral semantics. Okay, so we find the entities, and once we found the entities, each entity is an actor in Swim, which I also call a digital twin. It's an object, which is also a process somewhere in the fabric, and it is fed its own data, and it statefully reduces that data into a minimalist form.
Mm-hmm.
Swim captures as eventually consistent in terms of the actor state of all of the actors in the entire Swim fabric.
Mm-hmm.
And what we end up with is, if you imagine you had a database which had all the state of all the things, effectively that database is the state of all of the actors in this distributed system. And Swim has an internal format called Recon, which captures that. And what you end up with is you're trading off, the database and the cost of lookups and everything else. But it is a synchronization point with the eventual consistency of a fabric of loosely interconnected active actors, each of which maintains its own state.
So if it's maintaining its own state and you're thinking about application development, right, on top of this platform.
Yep.
That means you essentially can deploy an application architecture from that node, correct?
Well, so effectively what we're going to do is going to take this messy data, massively reduce it, and turn it into these active actors, these digital twins, which are going to analyze their own data, produce a whole squad of statistics and everything else about it, also learn on their own data and predict their own future, and present all of that information to you either as a pub sub type of API, you can consume it in that way, or you can query them. Okay? They also squirt out real-time updates to lightweight UI components, which make an easily composable web-based browser view.
So that's when the human developer can start to interact with the model.
Bingo. So now human developers, if they want to do anything more, are basically interacting with these actors which represent the system and its state and predictions. And so if you look at the UI in front of you, which is Palo Alto, that's it's 100 or 100 plus lines of code.
Yeah, it's a few hundred lines of code. And actually, it's worth noting this UI is a first-class part of the edge mesh. So when you sort of take this networked distributed actor system to its limit, and everything is a process, a communicating process, this web UI is actually going over the Swim protocol. We only use HTTP to serve up the page. We actually create a multiplex link to this edge mesh. And the UI looks like another device that links to these intersections and is getting fed the real-time data in literally the same way that the intersections are talking to each other. So this distributed fabric extends all the way to client devices, and it actually simplifies the problem of certain kinds of app development where you just need to bind UI view components to this rich real-time model that these digital twins have created.
So can you preserve state in these environments? Can you create, can you analyze this data and preserve certain states that you might find interesting?
Absolutely.
Could you apply that then to models to do, so I'm trying to think, so apply that to models to actually develop their own, modeling, analytics, whatever.
Yeah. So first of all, Swim is inherently stateful. Every digital twin is stateful, okay? The question is, do you want to remember all of the original data? And the answer is, yeah, what's the point, Let's just go for these sentient digital twins and forget the raw data, forget the big data construct, whatever you happen to be using, and forget the slow timescale data cleaning, data science exercises, and so on. Now, the right thing to do is to use the observations of these digital twins about their own future to record in a terse format their predictions or their analysis, which we do in exactly the same format as the data that came at us, so that you could use it for some other purpose. But goodness me, I keep on saying to Mark Rusinovich that Azure Data Lake should be called Azure Data Pond or Azure Data Swamp.
Yeah, so our goal is to remember what's important. So decide what is significant as quickly as you can to massively distill down the quantity of data you have to store. You can compress it over time, which cuts the size further. And then you can store quite a lot of historical context, and you can either sort of lazily. So we have one notion of sort of giving neural networks nightmares. This idea, one of the actually sort of risks with this continuous learning is you can sort of become less sensitive to sort of events in the distant past. So when a critical event occurs, like a car crash or a machine breaks down, you can choose to save that sort of imprint of that memory on the neural network and periodically play it back and retrain on it again to sort of like, which is kind of how I imagine the purpose of nightmares are, right? Like they don't let you forget that bad cloud experience or whatever. So you can I sound like perverse saying this, but you can give these neural networks nightmares so that they never forget the critical events that happen. And so there are other ways to incorporate historical context other than just storing the raw data.
Never forget.
Beware.
Beware. In any case, thank you guys for taking some time to explain to me a lot more about how to understand this node fabric that's emerging. And if I would only take it back a little bit, I would just say that it was the development in the cloud that has helped us start to think more about this.
Sure.
And that to me is the context here. And how it really matters in our own continual thinking through as we start to move, beyond, traditional application development process into more modeling behaviors, which to me is what is the story that we're going to hear more about. And this seems to exemplify that.
Yeah, I think you're spot on. I think the key thing is how to do the modeling without a modeler. That is, we just don't have enough people to model everything. Like, what's the model of my Tesla? Yeah, it's my Tesla. Let the darn thing compose its own model and then give me a high-level interface to query it.
Yeah, this story about analytics at the edge, about doing, I was talking to a group to the Open Source Leadership Summit about how they're building basically these new, they're building out basically a CDN architecture that can then, work with nodes at the edge to be able to keep, devices updated or whatever it might be.
It's a different beast. And if you look at it from first principles, you come to a very different conclusion than the cloud. It's not because anything that's done in the cloud is wrong. It's just a different beast. And what's sort of happening is reasoning by analogy of, well, this worked in the cloud, so there's a bunch of computers, it must work over there. But when you look at it from principles of how the compute is distributed, how the data is distributed, how diffuse it is, and the key is to build up from those principles the most effective solution that you can. And Swim is an attempt at that approach.
Well, that's, I think, what's fascinating about this time we're in. It's a continual process of refining your critical thinking, because if we're thinking more about how actually data interacts, it's it's beyond just one, central data center and out into this great beyond where the nodes are everything.
Yep.
So anyway, this has been a great conversation, you guys. Thank you so much, Chris Sachs and Simon. Thank you so much for joining us.
It's always a pleasure, a great pleasure indeed to be on. And thanks for all the wonderful work you do.
Simon Crosby, thank you. And I hope we get the chance for all of us to connect sometime. We should have you guys both back on our podcast to discuss these types of topics. So thanks for sharing your wisdom, and we'll talk soon.
Thanks very much. Enjoyed it.
Listen to more episodes of the New Stack Makers at thenewstack.io/podcast. Please rate and review us on iTunes, like us on YouTube, and follow us on SoundCloud. Thanks for listening, and see you next time.